Good morning, everyone. Welcome to the session, a deep dive into the current runtime security landscape. I am Ankur Kothiwal. I work at CERN as a computing engineer. I work in the Kubernetes team, maintaining Kubernetes clusters, and I also work on the registry aspects of it. I am also a CNCF ambassador and a project maintainer working with KubeArmor, which is a CNCF sandbox project. So today, we will talk about runtime security and take a deep look inside it. But before diving deeper, let's take what runtime security stands for. To define runtime security in one line, we can say it's detecting and mitigating threats in real time. And it addresses few vulnerabilities. It addresses vulnerabilities which are missed by static scans, or which can be missed by admission controllers, or due to human misconfiguration. And we have a lot of zero-day exploits. So for these things, runtime security is important. And then we have, and then we also want to ensure that the workload remains secure even when they are deployed. So all the things we discussed, for example, admission controllers and the runtime and the static scans, ensures that the workloads is secure before it is actually running. But we want once the workload is running, it should be secure during real time. So runtime security, if I quote, should be able to prevent or at least contain the attacks, and assuming that the attacker is already inside your cluster. So let's take a look at the out-of-the-box Kubernetes runtime security practices. So we have admission controllers, which allows enforcement before the request is reaching the API server, and we have a lot of admission controllers, for example, Kyverno or OPA agent. Then we have security practices like pod security standards and pod security admission. So under pod security I don't think, is it visible? Sorry for this. For pod security standards, we have different kind of policies. So we have baseline, restricted, and privileged policies. And these policies can then be implemented using pod security admission, which can define like whether you want to enforce those policies, whether you just want to audit the logs, or you want to warn the user that these were the policies which were violated, and not actually want to enforce those policies. And this is by default, this comes out of the box in Kubernetes. And then we have security context. Security context allows you to define a lot of good security practices, I will say, which will help you to secure your pods and all the containers running inside it. Under security context, you can define, for example, here I've defined privileged equals to false. It means that no workload will be allowed to run as privileged. And even if a workload is by default allowed privileged access, and it will not be able to escalate those privileges. We also have defined capabilities which are allowed by the workload. So apart from these capabilities, no other capabilities will be allowed. And this we can. And then we have defined drop all other capabilities. So we should only apply these kind of capabilities when we know what all Linux capabilities your application will be needing. Because otherwise, if it needs more capabilities than this, it might fail, or your application might crash. And then there are network policies for which you need different kind of CNIs, for example, Calico or Cilium. And inside this, you can have ingress or egress policies. And then you can define on what IP you want to block, or what ports you want to allow. But we are still missing something. Can you guess what? It is real-time protection. So how can we implement real-time protection or runtime security? The first thing which comes to my mind is observe what's happening and then kill it. Simple. How can we do that? So we have a few Linux primitives, I will say, and a few features inside Linux, which we can use for implementing runtime security. First of, one of them is LD preload, which allows you to execute dynamically linked executable before your binary. So if you want to have, if you want to change, for example, ls binary, you can point out LD preload equals to, you can define the environment variable LD preload, attach a binary, and then that binary, that library will run before your actual ls bin binary. We also have overriding glibc, which basically replaces the glibc library in the Linux. And then you can change glibc according to your needs. We also have seccomp, which allows to only run defined syscalls. And then we have ptrace, which is an observability tool and can intercept syscalls. And you might have noticed, OK, we also have fa-notify, which is used for file access monitoring and control. So all of these things we can use for observability purposes, and we can also use them for enforcement. For example, you can define a seccomp profile for what all syscalls you want to allow, and apart from those syscalls, everything else will be denied. You might have noticed that all of this is running in user space. So we call this user space-based runtime enforcement. We can do better by putting it in kernel. And we have BPF. So BPF allows us to observe and also allows us to enforce things. For observability, we can attach BPF kprobes on syscall entry, and then we can use BPF send signal or BPF override return for actually preventing things. So, but these two have some issues. For example, BPF send signal, you are sending a SIG kill signal from the kernel to kill a process. So for example, you see something malicious, you see it, and then you send a signal. It will be faster as you are doing it directly from the kernel, but still what you are doing is you are first observing something, seeing it's bad, and then killing it. And then we have seccomp notify, which is basically sending a signal from kernel to user space. And basically all the, I don't know if this should be in kernel space, but because seccomp is inside the kernel, but basically all the decision taking in seccomp notify happens in the user space. So enforcement is done in the user space, and observability we are doing in the kernel. Then we have Linux security modules. For example, AppArmor, SELinux, and relatively new BPF LSM. These allows us to define profiles or policies which can be enforced by directly from the Linux kernel modules. The issue with Linux security modules is it's very difficult to write. If you need knowledge of AppArmor, how it works, how to write the profile, if you want to write SELinux policies, it's pretty difficult. Then all these are not compatible with all the versions of Linux. So some might work in 6.2, some might not work. And then based on the cloud providers, it might differ which LSM might work and might not work. BPF LSM is relatively new. It works from kernel 5.7 onwards. And if you have like legacy code, you cannot run BPF LSMs. But did you notice the problem here in both the user space and the kernel space runtime enforcement? Absolutely. The fundamental issue is post-execution mitigation, which is just a fancy word for killing the things after observing it. So first we see malicious intent execution, we detect it, then there is a policy engine which basically kills the process, and then the first thing was attacker executing the binary. How can we solve it? Before going to that, let's see what does the current runtime security landscape look like, and what are the loopholes inside it. So all of these you will notice are runtime security engines. Some of them only do observability, and some of them do both observability and enforcement, for example, Tetragon and KubeArmor. And then we have a CNI engine, which also gives us a very good observability. And all of these, you might have noticed, utilizes eBPF, which basically allows you to run a sandbox program directly inside the kernel. So, and these programs are triggered based on certain events, which you can code by yourself. But there are a few fundamental issues with BPF. It's a relatively new technology, and it's getting involved. But there are a few things which might hinder in runtime security. First thing is eBPF probes might not invoke all the time, because there is a set limit on the active number of kret probes. Kret probes are kernel return probes, which basically are triggered when the kernel function returns value. And K probes and kret probes might have different callback logic, which can result in missed events. So you might miss a few events, and if you are doing enforcement based on that, you might miss some critical events. It's good for observability when you will receive a lot of events and you just want to know what all malicious things are going on. But if you want to enforce things and you miss some critical events, it's not a good scene. Then there is a limited number instruction count in eBPF, so the length of the eBPF program is limited. And then eBPF lacks concurrency primitives, so there is no locks, no mutexes, and which can result in talk-to issues. We will talk about it. And one more thing is attach points can be easily overwhelmed with events. So if there are a lot of events coming to a single attach point, it might get overwhelmed, and then after a certain limit, you might miss all the events after that. And attackers can use that for their own purposes. So Brendan Gregg has said this very nicely, that eBPF, to summarize it, eBPF is good for observability purposes, but if you are using it for enforcement and security aspects, you should take it as a grain of salt. Yeah, we talked about talk-to issues. So these are time-based race conditions, which basically happens when there is something changes in the code when in between when the thing is accessed and when it is being used, and this can be utilized by attackers for their malicious intent. For example, you check if this binary is allowed to be used. I'm just giving an example of talk-to attack. We check if this binary should be allowed to be used, and then we get, and then there is a lag between checking the permissions and telling the user that yes, it should be allowed. In between these things, these binaries or these files, these processes can be altered by the attackers, and we will never know if these are altered or not. And this happens when there is a latency between observability and enforcement. Yeah, we saw a lot of tools which used eBPF, and a lot of them only provide observability. So observability is not enough if you don't have enforcement. Yeah, it's a pretty good practice to, if you are just starting with security, you should know what's happening inside your cluster, what's happening with your workloads, if there's anything fishy. But once you know that, you want to do something, right? So observability alone is not enough, and you definitely need enforcement on top of that. Let's look at what attackers might use to circumvent these runtime protections. So they can exploit gaps in observability. So we saw that there are a few cases when you can miss events. If those events are missed, attackers might be able to do something fishy, which might not come in, which might not be enforced. Then we saw timing-based attacks. We can have misconfiguration and weak policies. For example, you have defined a very restrictive policy for your workload, but there are still some corner cases or some zero-day vulnerabilities which you might not know exist, and the attackers can utilize those. Then we have supply chain attacks, And there are few things in the kernel itself. We see from time to time there are multiple CVEs where user can bypass sandboxing and isolations. And this happened in the past with the BPF verifier, with kernel. So these are all the things which attacker can use for their own advantage. So now the question comes, how should we implement runtime security if like observing it and killing it is not good? Then what should we do? Observing is good, but instead of killing it, we should prevent what we allow to happen. And how can we prevent it? So first thing I will recommend is reducing the attack surface and deny everything by default. So only allow the things which you know will be needed by your application to run properly. And apart from that, deny everything else. Provide just the least set of privileges to your workload and ignore everything else. By doing that, you are not creating a policy which just have the cases which we should deny, but this is a policy which is denying everything by default and just allowing things. Then we should definitely use least privileges and the Kubernetes best practices. For example, running everything as non-root if not required, and in most of the cases, root access is not required when something is running in the deployment phase, and disallow privilege escalation. We can also define seccom policies for disallowing syscalls. This is not a runtime, like we are not enforcing something in runtime, but it's still a good practice. And then we should definitely do active monitoring. And then we talked about inline mitigation, which is basically the opposite of what we saw, like observing something and killing it. Inline mitigation says observes everything, but deny everything else, which is not required by your application. KubeArmor, the project I work on, is a really good example of real-time mitigation enforcement. What we are doing here is we are using these different kind of LSMs. As I said, the issue with these LSMs is the policies are difficult to write, and they might not be supported in all the platforms. So what we do with KubeArmor is you just write a human-readable policy, just a Kubernetes manifest, and under the hood, it converts those policies to AppArmor, BPF LSM, and SLNX-based policies. So you don't have to know how to use these engines. And then regarding the compatibility part, BPF LSM is one of stackable LSMs. What stackable means, it can be run on top of other LSMs. So BPF LSM can be run with AppArmor. But the issue in the past was that AppArmor cannot be run simultaneously with SLNX. So this helps us in expanding the compatibility aspect of it. So we support most of the kernels, KubeArmor. And you can protect both your node and your cluster. So with LSMs, the controls are applied even before the process is spawned. We are not killing something, but we are just denying everything, and we are just allowing the syscalls or the at the kernel level. So this is an example of inline mitigation, or things where we are preventing anything from mishappening. I will like to conclude my talk with these few points. First, we should focus on reducing the attack surface. This is really important. Like, if you have privilege allow in your on your pods, and you have like privilege escalation allowed, not have basic Kubernetes best practices in place, it will be pretty difficult for the runtime engine to also enforce any kind of policies. Then we saw like layer defense is good. There is not a single solution you can use, but you can think of it as using different kind of software solutions which can work together. For example, we saw BPF LSM, which can be used with other kind of security modules. And there should be greater emphasis on runtime prevention rather than post-execution mitigation. And runtime security is not about absolute prevention, but continuous adaptation, which means like it's not a one-time thing that you have deployed this runtime engine, for example, Tetragon or CubeArmor. It's like you are continuously monitoring and improving on top of what you are observing. Thank you. Any questions? Sure.
So, you mentioned that all these security policies are tough to write.
Mm-hmm.
The same thing I would say is that when you are saying that you are using setcoms, you need to identify which syscalls to allow and which not to allow. And then when somebody makes a change, and you need to go through the whole process again to see whether any new syscalls need to be added. So the real challenge also comes in the real, I should say the engineering side, where you want very rapid CI/CD sort of thing, you want DevOps to be, and at the other hand, because of all these reasons, you actually have to go back in the loop and redo everything. So how does one reconcile these sort of, where one has to exactly identify this change has happened because of which we need to add an additional syscall, let's say. Then it is really worth it or not, so you get into the paranoid loop. And at the other end, there are guys who are the future guys, the practical, who want to bring in the future ASAP. Then there are DevOps guys who want to, I mean, so the real, how does the one reconcile that?
Yeah.
Sort of a managerial act.
So your question, just to repeat for the audience who cannot hear you, is I said that LSM policies are difficult to write, but then I mentioned that you can write seccomp profile, which are also very difficult because you might not know which all syscalls you want to apply, right? So yeah, like you can only apply seccomp profile when you know what your application, what all the syscalls your application is using, and as I said, it's not a runtime kind of enforcement. That's why we have these runtime security aspects where we might not know what all syscalls your application is using, but then you can run any of these engines, for example, Falco, where you can see what all syscalls your application is using, and then you can observe it in your pre-deployment phase, and then see what all syscalls your application is using, and then in the deployment you don't apply it as an enforce policy, but instead you can apply it in warn phase. Right? So even if you are missing some kind of syscalls, if you will still get logs based on that, you will get warnings based on that, and then you can take decision for yourself if you want to allow those syscalls. And it's like a continuous process. Like it's not a like DevOps team and the engineering team, they should work together, and we call it DevSecOps. So everyone should work together on creating these policies, so that we have a policy which is not like breaking something in the production, right? Thank you. Thank you, everyone.